Welcome everybody. We apologize for the technical difficulties. I hope we have overcome them. Now we are ready to start. You have heard in the recent past other talks by Athanasios Tzemos in the frame of Bohmian Dynamics. And this is a continuation in this line of research. The talk of today is the role of avoided crossing and quantum scars in Bohmian Dynamics. And Athanasios starts immediately with his...
So, hello everyone from me. I apologize for the technical inconvenience. Too many of them now. I hope the internet, Professor Boudis, is stable enough. Half an hour ago it was not. So I hope everything is okay with Zoom.
Yeah, remind me. You speak from Panos. Yeah.
Yes.
Thanasi, who was the younger speaker who spoke about quantum
dynamics?
Bohmian dynamics last time? Fivos Anya. Right.
Fivos Anya.
I see.
Actually, the last time that I gave a talk in the center was in this date, July 2024. So this is the first ever of the talk. From then, we have published about 7 or 8 papers in Bohmian Dynamics and its comparison with classical Hamiltonian chaos. And actually, all of the results that have been published are already presented by Professor Kondopoulos in the last year and by Fivos Anias, which was the last member of our group during 2025. So, what are we doing nowadays? Today, I'm going to show you some very first steps, some baby steps that we are trying to do nowadays with Professor Kondopoulos. Fivos has finished his master thesis in Amsterdam. He has already presented it one week ago successfully. And nowadays, I'm left alone again with Professor, so I have to do all the dirty job for the calculations. And the main question, as always, in quantum foundations, if I can say so, is what is chaos in the quantum mechanics? Here we have published a series of works in Bohmian quantum chaos. As you know, this is interpretation of quantum mechanics which is based on trajectories, Bohmian trajectories, okay? So a highly non-linear and a highly non-local, non-relativistic quantum theory, which predicts the same results as standard quantum mechanics. But here we are familiar with trajectories since we are an astronomical institute, and we try to understand what is chaos in the quantum regime by means of the standard definitions. We already know, you probably know much better, many more things about classical Hamiltonian chaos than me. Nowadays, we believe that we know a lot of things about Bohmian quantum chaos. We know the standard definitions. We know what is the mechanism. We believe that we have found the mechanism for Bohmian chaos. But there is a bridge that is needed. We have to make. There's a gap that we have to bridge. What is the relation between the standard approximation of quantum chaos and the Bohmian approximation of quantum chaos? In the last July 2025 in Thessaloniki, there was a very nice conference, Dynamical Days Europe, where I found and I met Professor Marko Robnik from Maribor, Slovenia, who is a leading expert in quantum chaos. And I informed him about our job here in our institute. And we sat down for about a couple of hours. I presented him our works with Professor. He already knows Professor and from his work in standard chaos. And he actually told me a very simple question. So, okay, what is standard chaos and quantum chaos, and what is Bohmian quantum chaos, and is there a relation? Or there are two different worlds that cannot be connected? Okay, so nowadays that we know many things about classical chaos and Bohmian quantum chaos, we are trying to enter the field of standard quantum chaotic dynamics, which is already established, an established field established field for in the last 4 decades, 4 or 5 decades. Okay, so quickly, we know Hamiltonian chaos. We have the classical Hamiltonian systems that we know from astronomy. And these systems are governed by the Hamilton equations of motion. And we know many things about their integrability and their chaotic behavior and the coexistence of ordered and chaotic motion in a given Hamiltonian system, which is very nicely presented by the so-called Poincaré surfaces of section. So we see stability islands, we see chaotic seas, everything. And inside the chaotic seas, we have unstable periodic orbits, while in the center of the stability islands, we have stable periodic orbits. Okay, so what is the main measure, the main tool for calculating the chaotic behavior of trajectories, of classical trajectories, is the Lyapunov exponent, which shows the exponential sensitivity of these systems, of these nonlinear systems, to initial conditions. Okay, so since classical mechanics emerges from quantum mechanics, we expect the classical chaos to originate from quantum dynamics. So this is the quantum to classical transition. This is an open problem from the beginnings, from the generation, from the birth of quantum mechanics. Okay, what is the mechanism that takes us from the quantum regime and goes back to the classical, the macroscopical regime that we know from our everyday experience? So, does quantum mechanics contain chaotic dynamics at a fundamental level? As you know, in standard approximation of quantum mechanics, there are no trajectories. And since there are no trajectories, we cannot speak about chaos in a classical fashion. Okay, so we have to transform, or we have to modify, or we have to find new ways of approaching a kind of sensitivity in the quantum regime. So you have no trajectories. So then what is chaos? So a lot of work has been done of how we can find sensitive behavior in quantum chaotic systems, although they are governed by the Schrödinger equation, which is an equation about the psi, the wave function, which is something very difficult. It's fuzzy. We do not observe it in the
which is a linear equation.
Which is a linear equation. So there is no chaos by definition there. So how can we observe chaos in quantum regime? Here we have no exponential divergence of states, no sensitivity, non-linear mixing mechanisms. All the things that we know from standard chaotic dynamics are not here in a standard approximation of quantum mechanics that we know from the university. There are no trajectories, and the fundamental object is a wave function, as I told you before. So I'm in a rush. Okay. So the classical dynamical definition of chaos cannot be directly transferred to quantum systems. So now, what is the approximation of chaos in standard quantum mechanics? It has been shown in the last about 30 or 40 years that whenever a classical system exhibits chaotic behavior, then its quantum counterpart, if you solve the corresponding Schrödinger equation and see the statistics of the energy differences between successive energy levels, there is a correspondence between classical chaos and its quantum counterpart as regards the energy, the level spacing statistics. You find distributions of successive energy levels according to Wigner-Dyson statistics. While if the classical system is integrable, then you see that the corresponding quantum counterpart has energy gaps between successive levels distributed according to a Poisson statistics. And this is a well-established result in standard quantum chaos community, okay? So they try to understand what is the footprint of standard quantum chaos, how standard quantum chaos can be transferred in the quantum regime. And since we have Schrödinger equation, somewhere inside the spectral statistics, you can see the footprint of classical chaos. It's an interesting approximation. It's an approach. It's an interesting approach. Nowadays, there are many other tools. Phivos is not here. When Phivos presented his thesis a week ago, one of the reviewers, of the examiners, asked me, okay, why are you not satisfied with the quantum Lyapunov exponents? So I asked him, what is a quantum Lyapunov exponent? And is it something that has to do with a trajectory? No, it is not. So they try to understand in the quantum regime, if you have a quantum system, and if you take two operators that measure a quantity, okay, and you start by measuring a quantity here, which the first operator, V at V0, okay, and then you leave some time to pass, so the information in the system moves from one place to another inside the wave function. So they try to understand how information is moving inside the several parts of the wave function. So, for example, if you have an entangled state with many components, okay, if you have a spin chain and you ask what you measure the spin at the site 1 with an operator, and then you measure the spin 1 kilometer ago. This is a very long chain. After some time, you try to understand how information reaches this final point inside the system by altering the initial conditions. Which are the initial conditions? These are the parameters of the system, of the setup. So you try to change very slightly the initial parameters of the system, and you try to understand how the information, how the entanglement changes between the several parts of the system. So you have this tool that I'm trying to understand these days, the out-of-time ordered correlators. So you make here a measurement, and after some time, another measurement.
But if you change the parameters of the system, then you speak about two different systems, right?
Exactly. It's not the same. It's not the same thing. It's not the same thing exactly as in quantum mechanics, as in classical mechanics. You try to what is initial condition for a quantum system? It is its position in the Hilbert space. So you have to make some change in the definition. So if I try to ask what is a quantum state, it's not something very clear. So every system is accompanied by its Hilbert space. And with these kind of tools, they try to find how information travels inside the quantum system from a measurement point of view. And they find that they can they can see non-linear behavior, exponential sensitivity in this way. And in quantum mechanics, whenever two observables cannot be measured directly, this means from a mathematical point of view that the corresponding commutator is not zero. So you begin with a system that has parts that can be measured at the same time, and after some time they cannot be measured simultaneously. Okay, so this goes to this defines the so-called quantum of exponents.
Also,
if you have
Athanasi, αυτό το
corrections.
Που είπες το OTOC, πότε, when did it appear as a term, and who defined, who is working in this? I have not seen this.
I think maybe I'm wrong, but I think one of the main contributors is Professor Wisniewski from Argentina.
Yeah, how long ago, approximately? Is it recent?
10 years ago, 7 years ago. It's not
very familiar. Not very familiar
yes,
to me.
This is a new one. This is a new one. And if you try to understand it, if you write out of time order correlations in the Google, you'll see or in Scholarpedia, I think it's about 1 decade or less. It's a new measure. Okay. So, and I found it accidentally after the question of Fivos examiner. So we know now from in our center that we have Bohmian trajectories, which is an alternative approach, or not approximation, of quantum mechanics, where we have the so-called Bohmian trajectories. And here, whenever we have G going to 0, this is the place where we find the nodal points of the wave function, the places where the wave function vanishes, and the Bohmian trajectories are very sensitive around the nodal points. And Professor Kodopoulos with Christos showed back in 2007 and with Konstantinos Kalapotharakos and in 2009 that whenever a Bohmian trajectory comes close to a moving nodal point, then you have a second stagnant point of the Bohmian flow in the frame of reference of the moving nodal point, which is the so-called X point, and it scatters the Bohmian trajectories, and the successive and the cumulative effect of many such close encounters between the Bohmian trajectories and the X points is the generation of chaos. And you see it by measuring the Lyapunov exponent as Fivos showed us a week ago, 2 weeks ago. Okay, so you have the nodal point, X point complex, which is very familiar, which is well known to our center. So here you have the nodal point, and here you have the X point, and the incoming particles go this way or that way. Okay. So we have single node. Here I have an example of a nodal point trajectory. We have a wave function of a single nodal point, and this is its trace in time. So as you see, sometimes the nodal point moves fast and goes to infinity, and immediately after several increments of time, it comes from the other side. And here it's slow. Its velocity is small, while here the entrance, the exit is always very fast. So the nodal point, as you see it here, it's always accompanied by an X point in general. Okay, so we have wave functions with 1 nodal point, with 2 nodal points, 3 nodal points, n nodal points, or with infinitely many nodal points. Infinitely many nodal points, as in the case of qubits, where Fivos showed us that case, infinitely many nodal points, infinitely many X points. So it's a zoo, it's a mess. It's very difficult to trace the motion, and Bohmian chaos is everywhere. Another contribution to chaos that we found with Professor in 2023 was we named it the Y point, which is there are some times that in the frame of reference, in the original frame of reference, not in the frame of the moving nodal point, we have also their instabilities. And we found, like the X points, similar to the X points, stagnant points of the Bohmian flow, which are called the Y points. With this second kind of fixed unstable points, we managed to understand practically all the spectrum of the Lyapunov exponents in Bohmian trajectories. Okay, so here you have the production of chaos. I think Fivos showed that slide 2. So whenever you see the stretching number undergoing shifts, the Bohmian particle is always close to the nodal point or its X point. And here we have the corresponding distances. And the general fashion is, the general trend is that the X point is much stronger. The encounters between the Bohmian particle and the X point are much stronger as regard the formation of Lyapunov exponent than those with the Y point. Okay. So in the wave functions, we have different kinds, different numbers of nodal points and X points. And whenever we try to make predictions, we have to make initial distributions of Bohmian particles according to Born's rule. This is what the theory says. If you take the Bohmian particles and distribute them according to Born's rule, then you will find the measurement results already predicted by standard quantum mechanics. Okay, so if we try now to understand, these are old results, no new results, but it's just a quick review. We found that the wave functions, sometimes they are, the Born distributions, sometimes they are governed by chaotic trajectories, by initial conditions that will result to chaotic trajectories, and sometimes with initial conditions that will result to ordered trajectories. So there is an open problem that we try to understand. We have found many different cases. Here we have dominance of order. The red ones are initial conditions that will produce ordered Bohmian trajectories. Here we have about 50-50. It's another wave function of the same system. And here we have dominance of chaos. If you try to take very complex wave functions, then you will find many nodal points, X points, and sometimes you will see that chaos is practically dominant, about 100% inside the Born rule distribution. And now the new...
Wait a minute. Chaos is where here? Where the blue...
Yes, Professor. The blue points are initial conditions inside the Born rule distribution that if you integrate them up to a very large time, then you will see that they are chaotic trajectories. While here you see half of them being red, meaning ordered, and half of them being... While here, which is the single nodal point wave function, you see that order prevails, is the dominant trend.
Nice.
Okay, but here we have only one nodal point, so it's physically, it's intuitive to say that, okay, most of them will not feel just a single node, the presence of a single nodal point, so the close encounters should be fewer than in these cases. Okay, so if you have two oscillators, now we are going to standard quantum chaos. Okay, if you take two oscillators, independent, each one has its own frequency, omega 1 and omega 2. If you make a coupling between them, then the new system, the entangled, the connected system, has new frequencies, new canonical modes. Okay, these modes do not let the system to be studied separately, again, as in the case of independent oscillators. So you have an entangled system, even though we are talking about classical mechanics. And you have avoided crossings. The energy states do not cross one another. And in quantum mechanics, if you take a non-perturbed system, eta Hamiltonian is equal eta equal eta 0 plus a perturbation. Then, for example, the 2D harmonic oscillator. And if you take the Barbanis model, Kodopoulos-Barbanis model, okay, and add a small perturbation parameter, epsilon x y squared, epsilon Hipsy tetragonal, okay, you solve again the Schrödinger equation. You know perfect the spectrum of the 2D harmonic oscillator from Trahanas. Perfect. Okay. Now you're trying to do perturbation theory. and you solve it again. You diagonalize again the Hamiltonian matrix, and you plot the energy levels. You see that they are deformed. They, as a function of, you plot again the energy levels, the eigenvalues, as a function of what? Of the perturbation strength. And you see that they are curved. And sometimes, if you look them from far away, they seem to cross. But if you take a very good zoom, you will see that here there is no crossing. They can go arbitrarily close, but they will not cross each other due to the strong mixing between these two eigenstates, since you have interference and since you have the perturbation parameter. So the avoided crossings is a standard tool, is a standard phenomenon studied in the field of standard quantum chaos that shows that the classical Hamiltonian has chaotic behavior. So whenever you have connection in the interaction in the standard in classical chaos, you see the quantum system to exhibit avoided crossings.
Yeah. Thanasi, what I have seen in the many lectures they give about their own version with the of quantum chaos, I mean with the linear systems, the avoided crossings are not so close, do not come, in your case it looks like they intersect, but they don't, you say. However, the distance between them is necessarily so small there. What would it take to make them pull apart a little more?
I think, Professor, that this has, I don't know if I can answer it correctly, because it's the first time that I do these calculations. Whenever we, okay.
It's very interesting.
How do we solve the perturbed problem? Okay. Practically, I have to truncate the perturbed Hamiltonian in a set of states of the unperturbed problem.
Okay.
Okay, and this has to be done with a satisfactory accuracy. Okay, so here, where we have the perturbed 2D oscillator with the Barbanis model, okay, we start with irrational ratio of frequencies. You see that omega x is equal to unity and omega psi is square root of 3. Okay. So, by definition, you know that there is no
resonance.
Degeneracies. So the problem is not degenerate. Okay, and you try to understand. You see the orthogonal line, the red dashed line.
Yeah.
Inside this region of the figure, we have a great accuracy. For larger values of epsilon, we lose some accuracy. But yes, in the calculation of the energies. So we have an appendix in the corresponding paper where we try to explain that we do not need to make extremely large truncations because they are very they cost very much.
Inaccurate.
Yes, they are inaccurate, and if you try to make very good accuracy, to find very good accuracy, then you have to pay with a lot of time, computational time, which is not what we intend to do here.
But the distance between them is not within the error of course.
No, I think we calculated. Probably this is model based. We have to examine what are the systems that have been calculated. I don't know if you refer to such a system, because I think that most systems that have been studied in the field of standard quantum chaos are billiards.
Yeah. No,
these
I
kind
understand.
of things. Here we have a very simple system, which is actually it's a sub part of the non-Hiles problem.
Yeah, it just looks to me like they're crossing there, but you say that...
but it's not. It is not.
But it's not. Okay.
It's not. Okay. So we tried now to understand. Excuse me for being so talkative. We try to understand how the avoided crossings which are an effect of, which is a well-established effect of quantum systems, how they affect the Bohmian trajectories. It is very easy to say that Hamiltonian house has nothing to do with Bohmian house and stop there. But you have classical house connected with quantum house through the standard approach, 40 years of work, 40 or 50 years of work. And you have the Bohmian trajectories that we are trying to support here, that they are produced by the wave function. All the tools needed and all the properties measured in standard approach of quantum chaos have to do with the wave function. And the wave function is the mother of Bohmian trajectories. So it is not possible for them, at least in my opinion, not to be connected. How they are connected, it's a very difficult task. And I had a trip to Madrid before Christmas, where I met some experts in Bohmian quantum mechanics, and they told me that you are going inside the zoo and you're trying to bring all the order out of chaos. This is a mess because Bohmian trajectories are very complicated. However, they have to fill some way the standard quantum chaos. They have to fill the avoided crossings. They are generated by the wave function. So our idea with Professor is, how can we see? If we can see. We have to find a way. It's not very easy. Actually, it's very difficult. So we tried to produce the Bohmian trajectories of a wave function composed of terms that are close to the avoided crossings. So you see phi1, phi12, and phi13. Phi12 and phi13 are actually, I don't see it very clear here, sorry, one of these two cases. So you take a part which is phi1. Phi1 is actually the first eigenstate of the harmonic oscillator, and you take plus two parts that they are very close to each other at this value of epsilon. So you have you focus in a wave function, a very simple wave function. Okay, it's not a wave packet. A very simple wave function where the avoided crossing is living inside it, and we try to understand how Bohmian trajectories evolve in such a case. Because the very first works in Bohmian mechanics, we took combinations of eigenstates randomly. And actually, from a point of view that facilitates our computations. We want a single nodal point, or two nodal points, or three nodal points. Okay, now that we know the mechanism, we try to understand the physics. It's very complicated. It is still very complicated. And what we found is that in two cases where we had wave functions where 12 and 13 and 16 and 17 have avoided crossings at a certain value of epsilon, their Bohmian chaos was bigger inside a Born's rule distribution composed out of 5 or 10,000 of particles. So for each value of epsilon, you take a distribution. You run it, and you count the ordered and the chaotic trajectories. You raise up the value of the perturbation parameter. Again the same thing, and again the same thing, and again the same thing. And you see that whenever you have an avoided crossing, at least in the non-resonant case, we found a local extremum. And you see that close to this value of the perturbation parameter where the avoided crossing becomes minimum, they are actually identical, but they are not. The gap between them is extremely small, but it is not zero. Then you see that Bohmian chaos becomes dominant in a non-linear way. You have an extremum. And this is the only way that we can feel that the Bohmian trajectories can fill the house, the standard house inside the wave function. So I think I believe, maybe I'm wrong, but the dynamics has to do with the time scale in which Bohmian trajectories evolve. So what we found is that whenever you have an avoided crossing, Bohmian house fills it inside the Born distribution and shows a local peak. Okay. So we try to understand also the resonant cases where the circular frequencies are equal or are multiple integers of a standard frequency. This is much more difficult because here we have degeneracies. Whenever you have rational frequencies in the 2D harmonic oscillator without perturbation, then you have degeneracy eigenspaces. And you see a number of states having the same energy. And this, yes, parallel.
So in quantum mechanics, you have a relation between energy and frequencies.
Yeah.
This is why, I mean, when you have energy levels that come very close, are they corresponding to some frequencies that are very close?
Yes, when they are very close and they cannot be, they cannot cross each other.
They do.
Yes, they can if you have resonant cases or if you have extra symmetries that can produce crossings.
You have degeneracy in that case. When you have
Here in the resonant case, you see, I presented here for this exact reason. When you have epsilon equal to 0, you see crossings. This is not degeneracies, the different levels. However, when you insert the epsilon parameter, then immediately you see the breakdown of the degeneracy, the lift of the degeneracy. It's like a Zeeman effect, a Stark effect, something like that. Okay, and you immediately see avoided crossings. Okay. In
So
this,
the left picture was for epsilon equal to 0?
yes, Professor.
Okay.
If you see the horizontal axis, it's omega dio and not epsilon.
what are the
The colors are the different eigenspaces with the same energy. So you have, if you have nx plus ny equal 1, it is 0, 1 or 1, 0. So you have 2. So you have 2 lines. And these are the colors that represent the eigenspaces. But the next figure, the right figure, the degeneracy is lifted. Okay. Again, we found that here is not very easy to understand this example. We are trying to understand it. The resonances are not easy as the case of the non-resonant frequencies here, but again, close to the avoided crossing, Bohmian houses about 90% inside the Born distribution. Actually, this is not satisfactory to me. This is a strange result that we need to understand with Professor, but I can show it to you for now. And finally, okay, we have 10 minutes. Okay, and finally, now this was the results about the avoided crossings are under review in Physica Scripta, and we are waiting for the answer. And nowadays we have worked also in the quantum scaring effects. So what is quantum scaring effect? It has been shown in the past, and actually I think Professor Wood is that this has started back in the work of Heller in 1982 or 1983, the year that he was born.
That's right.
Yes, and then was Kaplan, another scientist, a leading figure in the field of quantum scaring.
Quantum scars was Eric Heller.
Eric Heller. Okay. It was shown that if you detect a classical periodic orbit of the Hamiltonian phase space that we know from astronomy, okay, for the classical Hamiltonian, you believe initially, the physicists believed that, okay, in the wave function there are several terms, and if you plot the probability distribution, the phi squared, the modulo phi squared, the probability density of finding a particle in this region of space, you will see something very fuzzy like being ergodic or something. But Edward Heller showed that there are cases where if you find the classical periodic orbit, then the probability density shows scars, amichef. It is the classical orbit underlies the probability density of the quantum system. So you trace the path of the classical orbit, and you see at this path that the probability density is bigger than expected. So you have peaks along the trajectory. So a lot of work has been done, and I'm trying to understand it these days in this field, in the standard quantum chaos. There are dozens of papers about that, okay, and they have been experimentally found. So it's very, very interesting effect, okay, and it is actually a well-established connection between standard classical chaos, because you know that you have stable periodic orbits in the center of the islands, but you also have unstable periodic orbits where you find the generation of chaos inside the chaotic zones, the chaotic seas. And Edward Heller pointed out that the unstable and not the stable, the unstable periodic orbits play a crucial role in the quantum scattering effect inside the eigenstates of the corresponding quantum system. So you would believe that, okay, well, I will never find such a result. Now quantum scattering effect is a prominent effect in quantum mechanics. Okay, so quantum scattering effect, 1984, in chaotic billiards. Quantum scars demonstrate that classical dynamics influences quantum eigenstates. They are not separate. Even unstable periodic orbits leave observable signatures. And chaos at the classical level is not fully washed out. It's not eliminated. Quantum mechanics fills classical trajectories. So here we tried to plot the probability distributions of the perturbed problem in the Barbanis model, okay? And with blue color, you see an unstable periodic orbit. And with red color, you see a stable periodic orbit. And you see that in this case, the unstable periodic orbit passes through the peaks of the contour plots. And this is actually the quantum scattering effect. And it's actually a very nice quantum effect that I think that I'm very lucky that I found it, because most of the scattering effects have been found in billiards. So you have a bouncing ball in a billiard and you trace its motion. Here we have a perturbed system, while in billiard we have a conservative system. However, we can see scattering phenomena even here. So again, we started with the non-resonant case, and then we moved to the resonant case. And here, what we do, what is the fashion what is the trend? How do we study the quantum scattering effects? You have a classical periodic orbit. Whether it is stable or unstable, what is the corresponding analog? The corresponding analog is a wave packet. So you take a wave packet centered around the classical periodic orbit, and you try to understand its motion, whether it is Bohmian or it is standard quantum mechanics. A wave packet is a combination, is a psi, is a wave function with a combination of many energies. Okay, and initially you initiate the wave packet around the periodic orbit. Here we have the perturbation. So we are waiting that the wave packet will be deformed, but maybe in some way it will fill the underlying classical orbit, whether it is stable or it's unstable. And here we show the participation ratio, actually, a quantity very well known in the field of standard quantum chaos, where when you have a wave function, combined of several terms, you see the participation ratio, the degree of the contribution of each term. And we measured with Professor that the scattering effects, in this case, the scarred eigenstates play a prominent role. And our final, we made the corresponding Poincaré surfaces of section of the classical system, and we detected with a very good numerical accuracy the periodic orbits, stable or unstable, with different degrees of multiplicity. Period 1, period 2, 3, or some anything that you can find here. And then we tried to understand what? You take again a Born rule distribution, 5,000 Bohmian particles, 10,000 Bohmian particles. You know that each, we have shown in the past that Bohmian trajectories, whenever they are chaotic, they acquire, they cover all the support of the wave function. The support of the wave function, although it is infinitely large, it is actually confined in a certain region of space. And the support practically is the place where you have remarkable probability of finding the particle. Okay, you can find it with non-zero probability at infinity, but you will never find it there. Okay, so all the chaotic trajectories, the Bohmian chaotic trajectories, are in this sense ergodic. What is the time needed for the Bohmian trajectories to cover the full space available for them? Okay, we found that with no exception, Professor Boudis, with no exception, each and every time that the wave packets around the stable periodic orbits reach their final ergodic pattern at greater times than those of the unstable, the corresponding unstable. Okay, this may be accidentally found. We tried to alter the physical parameters. We changed the frequencies. We changed the frequencies to become resonant. Two sets of values for resonant frequencies, two sets of values for non-resonant frequencies, and two cases of bifurcations where the stability of the classical periodic orbit changed from stable to unstable, and immediately the corresponding Bohmian trajectories felt the transition from stability to instability, and the times needed immediately changed. So this is
what is the difference again between red and blue here?
The blue one, here we have changed the colors. The blue one is the percentage of chaotic trajectories that have reached their final ergodic pattern inside a Born rule distribution of 5 or 10,000 particles as a function of time. And you see that the blue one is faster. The blue one corresponds to a wave function of a wave packet around an unstable and not a stable. Here the reds are the stable and the blues are the unstable. And we find this trend with no exception. Maybe it is a first result that is model based. We don't know yet. However, in our model, we never found an exception to this rule. So this is the end. Thank you very much.
The blue is faster. Tell me again, what is the difference again between them? I see one is more probable or more numerable.
It's more numerable. You have in both cases you have, let's say, 5,000 particles. Okay, and as the integration goes on, you count how many of the Bohmian trajectories have reached the borders of the ergodic pattern for the first time. They have covered all the available space for the first time. In the long time limit, they will go from the internal part to the external part many times. For the first part, the Bohmian trajectories around the unstable periodic orbit are more energetic, let's say. They tend to show their ergodic behavior faster than those.
The blue one, that's the blue.
Yes, the blue one. And
the
red one is the corresponding wave packet around the stable. Okay. So nowadays we are trying we make several experiments around about this effect, where we do not play only with the stability, but also with the degree of periodicity. You have two stable orbits. One is of period 1. Another one is of period 3. What are the corresponding dynamics in each case? And I do not take it for granted, but the degree of periodicity plays again a monotonous role, as far as I can see. So this is submitted to Physica D, and we are again waiting for the results. So this is what we do in the center nowadays with Professor, and every contribution is very welcome. Thank you.
Very good.
Okay, thank you very much. If there are more questions, please go ahead from the audience here.
Have you studied the pattern between for the change of time between the state in the state periodic orbits?
This is the
If there is a law, because if you take many cases, you can maybe there is something that is more
the law
follows a law. Maybe.
something like a power law or something like that. Not yet. I haven't done this. My only interest was in the stability. You change the stability. Do they feel?
Take many cases, maybe you can see something that you can measure.
Obviously, yes.
Cases,
Obviously, yes. That's why we are waiting for the Ferrier reports in order to see the first impressions, because we are newcomers in the standard quantum house approach. Okay.
Quantum chaos systems with Tzemos effect and Stark effect when you have perturbation of system.
Here we have a perturbation.
No, I mean about problems when you have a electromagnetic wave.
No.
That
Actually, this is the first work in Bohmian quantum mechanics. That
plan of quantum chaos. You said that quantum chaos you have in such systems, no?
Yes, if there are works in standard quantum chaos with Tzemos effect or Stark effect, I think there are dozens.
Really?
Yes, if not dozens, many of them, and there are yes. And actually, the most prominent works are still by Edward Heller, who is still active as far as I can say, up to 2020. Impurities, quantum scarring effects due to impurities inside materials. They are observed in the experimentally observed. These are not theoretical findings anymore. Okay.
For me, a very important result to have is the change with the bifurcation. And have you seen the change, for example, you have pitchfork bifurcation, period double bifurcation?
Even we have pitchfork bifurcation of period or period double bifurcation. In both cases, the change of stability of the first periodic orbit. So you go as a stable periodic orbit, and afterwards you turn to unstable, and you have the generation of two families of stable with double period. Immediately, the Bohmian trajectories change their time scale. And actually, this is what you told me 1 year, yes, a month ago or 2 months ago, because I tried to understand what kind of bifurcation is this. So probably this is resilient to the type of bifurcation.
Yeah, that's very important.
This is resilient to the type of bifurcation. The Bohmian dynamics or the wave function does not care about the type of bifurcation, but only about the change of stability. Maybe.
Not resilient, you mean maybe insensitive. It's not sensitive.
Insensitive.
It's not sensitive to the type of bifurcation.
Yes.
Scars you did mention. You do see scars in Bohmian dynamics.
Professor, scars are found in the eigenstates. You see the eigenstate, so you have to see the lobes here, and you see that the blue one is just a straight line and passing through the peaks of the contour plot. And if you take it in a 3D view, if you make the 3D probability density, it goes like a razor up and down the maxima.
Nice.
Well, this is a scarring effect. In order to observe scars, you do not always observe quantum scarring. There is a semi-classical theoretical background by Heller and Kaplan, which tries to explain the necessary conditions in order to observe quantum scattering phenomena. And this is directly linked and connected with the semi-classical theory by Gutzwiller back in the 90s, where Gutzwiller has pointed out the so-called trace formula, where you try to understand the spectral density of the energy levels of the quantum system and how this is affected by the number of the classical periods, periodic orbits of the corresponding classical system. This is a semi-classical approach. Okay, so the trend is that the unstable periodic orbits will play a prominent role, and they will play an even more prominent role whenever they have short period. There are many empirical findings about the stability of periodic orbits and their contribution to the quantum Eigen states. But it is a zoo, because you have different kinds of quantum systems. And in the classical phase space, in classical mechanics, you are working on a continuous phase space. You have variables in the macroscopical way of viewing the world. In quantum mechanics, you have the Hilbert space, so you have another mathematical framework, and you have discrete quantum energy levels. That is why Asher Perez back in the 90s used to tell that whenever you try to understand or to use the correspondence principle started back in the 20s by Schrödinger, Pauli, and the other leading figures of quantum mechanics, you will find many cases where the correspondence principle does not apply. So the problem is always open. What we try to understand are the phenomenology, at least for the first time.
That will be very interesting to do this in Hamiltonian system with 3 degrees of freedom.
Ωραία θα ήταν. Ωραία θα ήταν. Αλλά θα το κάνεις εσύ. Θα μου τα πεις και εμένα. Αυτά.
I often hear from my friend εκεί είμαστε τώρα, βλέπω όλοι οι Έλληνες στο...
Όλοι οι Έλληνες. Yes, but it is better to speak in English because it's recorded.
Okay, very good. I often hear from Marco Robnik and many of his colleagues in those meetings we had in Slovenia about the distributions of spectra and different kinds.
Poissonian or Wigner-Dyson.
Poissonian, Wigner-Dyson. Do you have such effects here? Can you?
I haven't calculated here, but if you ask me about the Poisson, whether they are Poissonian or Wigner-Dyson, actually they are Wigner-Dyson because we have.
They should be, yeah. Poisson is integrability. Poisson is integrable.
Poisson means integrability, while Wigner-Dyson means complex dynamics.
Right.
The main problem, as regard myself, is how to unfold the energy levels in the quantum system. The energy levels of the harmonic oscillator do not have the same density as you moving up the ladder, you moving up the quantum numbers. This means that it is very easy to make wrong predictions if you do not unfold or do not normalize the spacings between the energy levels. So the probability distributions, P of S is the normalized energy level spacing between successive levels. And this was pointed out to me by Professor Robnik.
Exactly. You had this conversation with him. That's why I expect he told you a lot of things like that. And also the Poissonian, which is close to integrability.
Whenever you have a Poissonian, Professor Boudis, it's an exponential of minus S. So whenever S is small, you find a great probability, a remarkable probability. But whenever you have a Wigner-Dyson, you see a Wigner-like form of probability for the low levels. So
Right.
if you try to find very small energy gaps,
Yes.
the probability in Poissonian statistics is much larger than that of in the corresponding Wigner-Dyson statistic. Because the Wigner-Dyson is S times exponential minus squared S. While
Yes.
the
Sure.
Poissonian is exponential of minus S.
Right, but okay, you don't want to take an integrable system, but you, as they do, they take the integrable billiard, whatever.
Yeah.
But if you have anything coming close to Poisson, if you have a very small chaos in your
Very small
equation,
perturbation.
it's very small perturbation.
Mm.
Does the spectrum look a little bit like Poisson of the?
Yes, actually, it's I think that is the case of weak chaos. If I'm not,
Yes,
I'm
but
not wrong.
you see something like that, huh?
Yes, you see something like that. But I don't know. I cannot transform it. I cannot translate it to Bohmian house.
Sure.
For now, I have no answer.
No way to make that.
Yes.
Very good. Well, the point is that I'll tell Marco to invite you to Slovenia next winter. Next winter.
Okay.
If you impressed him enough, he will certainly invite you next Christmas.
Yes, he asked me, are there any works about Bohmian quantum mechanics and about Bohmian chaos, and I gave him about 25. So.
Yeah. Okay, very good. Λοιπόν, γεια σας, παιδιά. Ευχαριστώ πολύ.
Γεια σας.
Ευχαριστούμε πολύ.